Our last topic for properties of amines is basicity. And we also have a worksheet on basicity. What we want to be able to do is look at a couple or more structures of amines and rank them in order of weakest to strongest base. Amines are bases because they can be protonated. And a lot of amines are amphoteric, meaning that they also could be acids, but amines definitely prefer to act as bases, and giving up a proton is a pretty difficult experience for an amine. Here's just in general, I'm going to draw a tertiary amine, but this could be any of the amines, primary, secondary, or tertiary. Any acid, I'm going to use hydrochloric acid, because there's that lone pair of electrons on the nitrogen. You can always stick a proton onto that nitrogen positive charge. And so because of this, this is the definition of what it means to be a base, a proton or an H plus acceptor. Before we get into the worksheet, really what I'm going to do is just kind of like basically review the entire Chem 163 class in probably 3 minutes. The most important parts of stuff that you learned in Chem 163. So when we're ranking or quantifying the acidity or basicity of something in 163, you learned to do that using either Ka or Kb. Ka if it was an acid, or Kb if it was a base. In organic chemistry, we almost exclusively just deal with Ka. Everything can be described in terms of Ka. One of the things you learned in 163 is that there is a relationship between Ka and Kb, that Ka times Kb equals Kw. So whether you have an acid or a base, you can always figure out it's Ka or it's Kb, one or the other. Everything has a Ka and a Kb. So just to keep things simple, all of our data tables are in terms of the acidity, so it's Ka. And in fact, to keep it even more simple, all of our data tables are actually in terms of pKa, because if you recall, pKa is an easier number to look at than a Ka. So what I want to do here is just remind you where pKa comes from, how we can look at pKa and kind of relate it into a pKb, and the relationship between the value of the pKa and the strength of the base. And to do that, the first thing I want to do is remind you, let's go all the way back to the beginning. And what is Ka? Ka is that equilibrium expression where we're doing the concentration of whatever the products are over the concentration of whatever the reactants are. And so if we have a strong acid, by definition, that means that we have a lot of products. And the stronger the acid is, the more products we have. So for a strong acid, if we have a lot of products, if that's a big number, the value of Ka is high. So strong acids have big Ka values, and weak acids have small Ka values. All of these numbers are something times 10 to the minus something. In general, they're all very small numbers, and so that's why we introduced the concept of pKa, which is the negative log of the Ka. And the pKa, I don't know if this was explained to you in 163, but the pKa is just essentially the exponent of the Ka. So for example, if our Ka is 1.8 times 10 to the minus 5, our pKa is going to be approximately 5. It's a negative exponent, not the exponent. So, and that's an approximate. In this case, the pKa is actually 4.6, but that's pretty close. So the pKa is essentially the exponent, the negative exponent of the Ka. So if we have a small Ka, going back up to this stuff right here, If we have a small Ka, that means that it is going to have a very negative and small exponent. And this is going to give it a big or high pKa. Very negative exponent, like a negative 20 is going to turn into a pKa of like 20. Negative 50 is going to turn into a pKa of like 50. So the smaller the Ka is, the bigger the pKa is. So we've got that relationship. And then another thing that you learned in 163 is that if something is a strong acid, it is also going to be a weak base. Or if something is a weak acid, then maybe it's going to be a strong base. And I don't mean that in the sense of the actual definition of strong acid and strong base. So maybe we should say stronger acid is a weaker base and a weaker acid is a stronger base. So we don't confuse it with strong acid, strong base. So what can we get from, we've got one more thing we have to remember. pKa plus pKb is always equal to 14 at that right there. So keep that in mind as we're doing all these things. So putting all of these different points together, all of these different facts and truths that you know from 163, if we see a molecule that has, if we're ranking and we see a molecule that has a high pKa value, a high pKa value is right here. That means that it has a small Ka. And if something has a small Ka, that means that it's a weak acid. And if something is a weak acid, that means that it's a strong base. And when we're in a chapter where we're talking about amines and we're focusing on bases, right here, high pKa is a stronger base, stronger. That's like the take home. Low pKa is a weaker base. So this, if we have a table of pKa values, we can use this to rank a set of amines in terms of their basicity. And in your textbook, you have 3 tables with pKa values in them. And this is one of the tables. In this table, you're getting the structure of an amine. They're also, just for your own reference, they're showing you the structure of the protonated version, but then they're also giving you the pKa value, which you can use to rank if you are looking at any of these amines. You can use these values to rank any of these amines. This table continues, so it's spread out over 2 pages. This is table 23.1, and in my book, it's on page 1110. And then we also have this one, which is a table of aniline derivatives with their pKa values as well. So this is kind of handy. It's not going to help you out a ton when you're doing rankings, because when you're doing problems on sapling, for example, the odds of finding one exactly like one of these is pretty slim, but it gives you at least something to start with, like a starting point in terms of ranking amines in order of increasing basicity. We're going to practice it quite a bit.